we'll now build on the concepts we discussed in the past two videos to redefine a concept that we've introduced so far in our course. All right, and so we saw that if the number of objects or particles in our system was very large, so let's say we had times 10 to the 23, so Avogadro's number of particles in our system, we'd expect that the number of different ways we could arrange those particles in our system is going to be very large. Okay. All right, and so that's, a really big number. And even just kind of like thinking about that number or manipulating that number is going to be kind of very abstract and very hard to manage. All right, and so to make our discussion of the number or the number of ways we could arrange the molecules in the system, to make that a little bit more tangible, so more manageable, what we're going to do is we're going to define an equation, I guess I'll say. Define the following term. Okay? So what we're going to do is we're going to take, we have a very large number, and to make it at least a more manageable thing, we're going to take the natural log of it. Okay? All right? And so this natural log, we're then going to multiply it by what we call Boltzmann's constant. I'll talk more about that in a bit. All right? But essentially, and Boltzmann's constant here just has units of joule per molecule per Kelvin. Okay. All right, and so this equation right here, this very kind of simple equation, this Boltzmann's constant times the natural log of the multiplicity, we're going to call this S. All right, and we're calling that S because this equation calculates entropy. Okay? Yeah, so this is the same S that we've been talking about since chapter 4. All right, and so when we consider molecules and when we're considering systems at the microscopic level, whenever we talk about entropy at the microscopic level, all it is just the logarithm of the number of different ways of arranging molecules in a system. Okay? Right? And so the reason it's this, so entropy, the only reason it exists is because we don't really want to work with large numbers, and so all we're doing is just taking the natural log of it to make it a smaller, more manageable number, but it still contains the same amount of information. Okay? Now, this Boltzmann's constant here, you may have seen it before, but why is it here? It's there for the same reason that we saw Planck's constant before. That is, from classical thermodynamics, we know entropy has units of like joule per mole Kelvin. Right? And so if we want, for defining the natural logarithm of the multiplicity as entropy, we also need to figure out a way of getting back those same units. And so all we do is just multiply by Boltzmann's constant. Right? And it gives us units of joules per molecule per Kelvin. Boltzmann's constant, if you don't remember, is 1.38 times 10 to the negative 23 joules per molecule per Kelvin. right? And so this is a per molecule number, right? So this is the entropy. This equation that we're seeing here is the entropy for arranging one single molecule in our system. But if we multiplied that, equation by Avogadro's number, moves down here. If we multiply this by Avogadro's number, we would see that the units we get for this, so Avogadro's number is the number of molecules per mole, so let me rewrite this to be clearer. NAV is Avogadro's number, and that has units of molecule per mole. And so when you multiply Avogadro's number by Boltzmann's constant, what you get is joules per mole K. Or otherwise, this product is known as the gas constant, right? This is the same gas constant that you've seen forever. So Avogadro's number times the Boltzmann's constant is the gas constant. Okay, and so this sort of definition would then give us the molar entropy, which has units of joule per mole K.